because the erosion question is not coming. But here, in the design of unlined canal, this erosion is coming very much. And of course, in case of non-alluvial channel, where erosion is not that much significant, it can be significant or it becomes significant when the velocity exceeds a particular limit, and that we call as a maximum permissible velocity. So in non-alluvial channel, our design principle is that our velocity should not exceed a maximum permissible velocity. And then of course, if it carries some sediment, which is not a regular problem of non-alluvial channel, but still if it carries some sediment, in that case, the velocity also must exceed a very minimum velocity, which will not allow sedimentation if that water carries sediment or if sediment-laden water come through the channel. Well, that was the discussion about non-alluvial channel, and today we shall be discussing on alluvial channel. And of course, we started discussion on alluvial channel earlier. And on alluvial channel, our main criteria, the design criteria is the concept of critical velocity that we did discuss in the last class. The critical velocity we mean here, it is the non-silting, non-scouring velocity. That means we need to have a velocity, we need to have our size of the channel in such a way that the dimension of the canal should be such that the flow velocity will be of the type that it will neither cause scouring of the channel nor it will allow deposition of the silt that is flowing through the canal. And that sort of velocity, achieving that sort of velocity is of course very difficult, that we discussed in detail in the last class. But still, people are trying, and then the person who tried this design first is the Kennedy. And then he was doing this by observing several stable channels in the region of Upper Bari Doab, which is located in Punjab. Of course, Punjab means now it is in Pakistan, in that part. And then by observing some stable channel, he gave it. And then, of course, then this theory had a lot of limitation, and then Lacey's theories came up, and that way we are now working on alluvial channel. Of course, nowadays, then all this formula, like Kennedy's formula, Lacey's formula, all these are basically empirical formula that is based on observed data. These were derived based on observed data. But after that, people started working on possibility of having some analytical solution, or at least to have some analytical basis, although the things may be designed or some parameter may be coming up from some observed value, but still that there should be some analytical basis. That way some semi-analytical approach can be adopted, and say tractive force method is one of such methods. So we will be discussing all those. Well, let us just start with some of those important issues of Kennedy's silt theory that we did discuss in the last class, but still we will be just starting from that aspect. So you can concentrate on the slide because we will be showing the formula here basically, that it gave this theory, he gave this theory based on his observation of several stable ridge, I am underlining this one, several stable ridge of Upper Bari Doab canal system of Punjab and now in Pakistan. Then he measured the flow velocity. Actually, after getting those stable ridges, he measured the flow velocity and he named this as V0. So this V0 he measured, and of course he considered that this V0 velocity will be having a relationship with the depth of flow. That means if the flow velocity and depth we observe, then we find that the channel remains stable for a velocity, and at that velocity if the depth is having a particular value. So that way he tried to relate this depth and the velocity, and at that point he considered that the width of the channel has nothing to do with this relation, and then relating this V0 and the depth D, he plotted this data in a curve, and then after plotting these things he derived this particular relation, that is V0, velocity V0 is equal to 0.55, then D means depth to the power 0.64. Means suppose if we plot the V0 in this direction, I'm just giving one example, say V0 for all those stable channels. Suppose several stable channels are there in the upper body drop canal portion. Then he observed, then he found that some D0, he is measuring depth, and then at the same time, for that particular portion, what is the flow velocity that he is observing. And for several years, that he found that for several years, this particular channel is stable. And that's why he took those channel portion. And then, say, putting this V0 and this D, say he is getting a curve like this. Well, exactly what sort of curve he got, that is not a question here, but suppose he got several points, and say, for example, I am giving, suppose the points can be plotted like this, and the equation of this particular curve may give us one relation or equation. So that equation is, say, this one, V0 is equal to 0.5 D to the power 0.64, where this V0 is in meter per second. This V0 is in meter per second and D is in meter. Okay, so this was the popular and famous formula of Kennedy. And then he, as I said, that he didn't consider the effect of, this width of the channel on critical velocity. And then, in fact, to introduce the effect of sill size, here, as you can observe in this formula, this velocity, he is saying that this velocity is the critical velocity where no erosion, no deposition will take place. And this depth is only the parameter on which he is deriving this velocity. But from our general concept, we know one thing, that at a particular velocity, whether there will be erosion or whether there will be deposition, that will definitely depend on the silt size. If the bed material that is consisting of very fine silt, then at a very low velocity also this can be eroded. If it is, suppose, a larger size silt, then it may not be eroded. So that way the silt will definitely have some influence on the entire relationship. And when he initially observed, he didn't consider those effects of silt, because the very reason is that he was observing this value only in the region that is the upper buried drop canal system. And for that canal system, the sediment size or the silt size of the canal are same. Identical. In all the channel reach, he considered these were same. So what he observed, that he got the same value. He got that, okay, this relation is valid. But if we put a different kind of silt, then definitely the relation what he obtained will not be valid. And that he could realize later when this formula was attempted applying in different area, having different silt grade. By silt grade, we are meaning, say, silt size. What is the proportion of silt size in a particular silt sample? And say, what is the average size? Say, we call it as the D50 average size. So that way, this effect came later. And so to introduce the effect of silt size, later he introduced a factor M, and this factor is called critical velocity ratio. He named this as critical velocity ratio. So what this ratio is, critical velocity ratio, that if we see that this M was introduced, which is called critical velocity ratio. Well, so M means it is V by V0. Now what is V0? So V0 is the velocity or critical velocity, say we can write it as critical velocity of upper Bariduak channel region, critical velocity of upper Bariduak canal region, canal system, upper Bariduak canal system. And then this V is the critical velocity somewhere else, means the place under consideration, Okay. Well, by this what we mean that, say, if we know the critical velocity for the upper Baroudov canal region, then we can find the critical velocity in other place. Or indirectly, if we know the m value, for a particular region or a particular type of sediment, then we can find the critical velocity for that particular place. So when m is greater than 1, then it is greater than 1 for silt coarser than the upper Baroudov canal region. So that means for suppose upper Baroudov canal region, we have a V0 value. Then if the silt size for a different region is greater than, or the size is larger than the upper Baroudov channel region, then definitely the critical velocity will be larger. It will be, say, erosion, that means the larger velocity will be required for eroding the channel. So that way it will be larger, and that's why this m value will be greater than 1. And if your silt is finer than the upper Baroudov canal region, then this m value will be smaller. And so then people are investigating, and different other followers are working on that line, and they have given some value for m also for different part of the country. And then definitely for using this equation, we should not use directly in a particular region. Once we are sure about this m value, say this equation was developed in the region of Punjab. Now if we want to, which is on the, say, western part of our country, and then if we try to apply that equation in the suppose eastern part of the country, then we should conduct some experiment. Then only we will be knowing that, okay, this will be the m value for this particular region, and then only we should apply this formula. Of course, this Kennedy's formula has some of the limitation. And then what is the procedure? How we basically use Kennedy formula for designing our canal? Well, so the basic equation that are used for design are continuity equation. That will be required. That means along with the Kennedy's equation, we'll be requiring some of the fundamental equation for design of the canal. And continuity equation, as we know, that this is equal to Q is equal to A into V. And then we should use the uniform flow equation, because this canal we design for uniform flow condition always. And so uniform flow equation, again, there are several uniform flow equation, as we know, that Manning's equation, Chayes' equation, then Cutter's equation, Bazin's equation, different equations are there. And now while designing this canal, people generally prefer the Cutter's equation. They use the Cutter's equation. Well, but of course, we can try with Manning's equation also. Basically, we need one relationship, that is to know that, so that we can express V in terms of the other parameter, say R, that is hydraulic radius, roughness parameter, say now I'm writing as 1 by N, and the slope. And based on all those parameters, okay, if I write Manning's equation, it will be 2 by 3 s to the power half. So as B. And R is the ratio of area by perimeter, as we all know. And that means R is a function of what is your B value, what is your Y value. That means what is your width and what is our depth. So based on that, we can express the velocity. So this is one relation that we know. And then, of course, our main equation for design of the canal, that is the Kennedy's equation, that will be required. That is V0, as we are writing this one, is equal to 0.55 m and d to the power 0.64. And this is in metric unit, that is the d is in meter, V0 is in meter per second. Well, but in this entire computational process for designing the channel, there is no mention about the slope. That means if we if we calculate our size of the canal, here we are not considering the bed slope, particularly when we are using the Kennedy's equation, we are finding that this is the V0. If we assume a depth d, and then we are calculating the critical velocity. Then once we get the critical velocity, we can get the area of the canal. Then from the area of the canal, area is again a function of b and y. So y means the depth I am talking about, and here of course we are using the symbol d. So in this place also I can write d in place of y. Okay, so depth. So depth is already known, so b we can calculate, and then calculating the b. So once we get d and b, then using this d and b we can calculate r. Then of course the bed slope will be known to us. Bed slope will be known to us. So for that bed slope, we can now calculate our uniform flow velocity, v. We can use Cutter's equation also, as it is very lengthy. I am just writing the Manning's equation here. V we can use. Now, so for our requirement is concerned that we are considering this is to be critical velocity. But when we calculate by using uniform flow formula, after getting b and d from this continuity equation and this Kennedy's equation, we'll be getting another uniform flow velocity. But if these two velocity are not matching, that means our design is not correct. We are considering something to be critical velocity, but in reality we are getting something else, because the flow velocity what we are getting by using uniform flow formula is actually the velocity what we will be getting in the field. So it is not matching. That means the d what we assume, initially we assume a d value, or rather we take a trial value of d. So the trial value of d that we did take is not correct. So what we'll have to do, we'll have to change the d value. Well, that means for that d value, we are not arriving into a position that our uniform flow for velocity what we are getting is not matching with the, or it is not becoming the critical velocity. So that d will not serve our purpose. So we'll take another d, and then we'll again calculate our v0, and then with that v we will be finding area. Then again we will be getting b and d, that is the depth and width, and we are again trying what actually we are getting in the field by using the uniform flow formula. So that trial and error procedure is required here, and once we find that both the v is matching, then we are getting that yes, our the channel what we are proposing, the design what we are suggesting for b and d are of course acceptable. So that is what the basic procedure is. But in this formula we are not talking about anything about the slope in the Kennedy's formula. And then later, and of course we are calculating the b and d based on the continuity equation. Then later Kennedy, he realized that no, there is a need of putting some relationship or some proportion of b also, because when he is equating, when he is trying to find this critical velocity with respect to d, then at the same time he found that a b by d ratio can be given. B by d ratio can be given. That if this is the d, then this should be the b. Then only the channel will become, say, stable. So based on that, some experimentations were carried out, and so departments of Punjab area at that time also they conducted experiment, and they gave some b by d ratio. Now, what is the advantage of having this b by d ratio? Because earlier also we could calculate our ultimate size of the channel, because which match with this v, that is the Kennedy's velocity and the uniform flow velocity. So that we could do. But as it was stated, I have also mentioned that slope was not considered at that point. We are considering a slope which we are getting from the natural terrain, that is from the topography of the channel, rather topography of the area. We are considering that okay, this is the slope we can provide. But always there remain a scope of adjusting the slope to some extent. That is, I was explaining that part earlier also. Say, well, let me take some space. Say this is the area, and they are supposed to carry the water from this point to that point, say point A to point B. We want to construct a canal. Now we can make the canal, suppose we are starting digging here, and then we can make the canal like this. Or one can feel that no, he will go like this, he will go like this. And then another may think that okay, we'll do some, then in this case he is cutting this much, depositing this much. In this case he is cutting here a lot but no deposition, and he is going like that. So that there is a scope of adjusting the slope to some extent, and that we cannot achieve when we do not use rather B by D ratio. Then we do not have the scope of adjusting the slope. Now when we use B by D ratio, then what we can do, we can use this B by D ratio to find, once we can find, we are assuming a D. So now considering that B by, so from that we are getting a V, and then from the B by D ratio we will be getting a B also. And using that B, we can directly put it, using that B, now we can just try to see that if we adjust the slope with that B and D value, can we get this velocity? So we'll try adjusting this as B, and with some adjustment of this as B, we'll try that if we can have the, because once we get this, once we assume this D value, then as we have a B by D ratio, so both B and D are with us. Now putting this B by D, we can get this relation, and then we can try to see that whether we can adjust this value or not. Of course, this Q is our prime requirement because we are trying to put that much of discharge. So this Q is equal to A into V will have to be satisfied. Well, so let us see step by step what we should follow. I have explained it briefly, and now in step by step way what we can do, that first we need to assume the depth D. Well, so depth D we are assuming. Then using the Kennedy's method, we are computing the velocity V, that is the critical velocity we are computing. Then we are computing the area from the continuity equation. Well, then from known area and D, that is the depth D, then we need to compute the width B, that is the bed width B. Of course, when we are using this Q and this, our shape can be trapezoidal, shape can be rectangular, anything it can be. That we'll have to decide. Again, we did discuss about that part also, how we decide the slope, that we'll have to do. Well, then next step is that compute flow velocity using uniform flow formula. This uniform flow formula can be Cutter's or Manning's, but basically Cutter's equation is preferred here. Then we should compare the computed velocity with Kennedy's velocity. Computed velocity means this uniform flow formula, what velocity we are getting. Then from this step we should go for iterative procedure. So adopt iterative procedure and have the correct value of T, so that both the computed velocity by the Kennedy method and by the uniform flow method, that become almost equal. Of course, we can go for almost equal. Exact value may not be matching. So this is what the procedure is. And if B by D ratio is given, one can adjust the slope to have commensurate value of velocity. So commensurate value of velocity means, again, these two velocity should be almost equal. So that is what the steps that we follow in Kennedy's theory. Well, after Kennedy's theory, the next theory that came is Leslie's Resign theory. We just gave the name earlier in the last class, and then we discussed the originally when it was developed and all those things, so we are not going to that part. But his principle is the Resign Channel. His principle is the Resign Channel. I mean, of course, it is similar to having a critical velocity, but what he is suggesting that for a particular size of the channel can be regarded to be in Resign condition. And naturally, if we allow, what is Resign condition? Naturally, if we allow the water to flow in a channel, then depending on the flow velocity and the size of the channel, it may happen that if it has the erosive power, the water will have erosive power if the flow velocity is high. Then it will start eroding the channel. in alluvial channel I am talking about. So it will start eroding the channel. And just the reverse, if we think that if it is the size of the channel is very large and the flow velocity is very low as such, that means we are talking always about all this fact when we are talking about a particular discharge. So for that discharge, if our flow velocity is very less, then as it will be carrying some sediment with it, because it is an alluvial channel, so sediment is a must. I mean, sediment will have to flow through the water. So that's why then those sediment will start depositing in the bed. And then, so ultimately what we can see, that if we allow a channel to run for a long time, it will adjust its own size. The width may increase, the depth may increase, or so due to sedimentation, width may decrease and depth may decrease. So that process will continue. And after continuing this process for a very long period, it will come to a stage that it will not change its width or depth further. And that condition is referred as, say, resign condition. That condition is basically referred as resign condition. Well, so as a definition of resign condition, we can state like that